This is the AcousticEye software application. It's being used both for acquiring the measurements and for analyzing the result. In this short demo movie, we will do a short step-by-step guide for creating an inspection session and analyzing the result till the creation of a final inspection report. Our first step is at the Setup main tab, which is all the pre-measurement actions. We start at the most left subtab, the Map tab. The regular flow of the software is very simple, going from left to right. In the Map subtab, we create the map of the tube sheet we are about to measure. Using the software, we have several ways of performing it. We can, for example, scan a schematic of the unit we are about to measure. But the most useful way of creating the tube sheet map is using a sub-application called the Map Builder. On the Map Builder, we can simply load a digital image of the equipment that we already taken, and then using the software interface, simply mark the tube that we want to measure. Here I need to adjust a bit the size of the circle, and then I can easily and quickly continue to mark the tubes I'm about to measure. By doing that, I also determine my inspection path, whether I want to start from right top and go left, and so on. Once it's done, I can just save the customized map and close the Map Builder application. Back on the main software, I can choose the custom folder, and here I will find the map that I just created. My next step, by going according to the left to right flow, is just inserting the parameters of the inspection. All I need to insert is the length of the tube, its outer diameter, wall thickness, the adapter that I'm using, and the inspection temperature. Next, I can fill in some general inspection details that will appear in the final inspection report, like the date of the inspection, the site, the customer name, and so on. I can also enter the name of the service providing company that performed the job and its logo. Those two details will appear in the top of each page in the final inspection report. Once it's done, I can simply go to the next main tab on the right, the Measurement tab, where the inspection is actually being performed. Performing a tube inspection using the AcousticEye system is very simple. All I need to do is simply to insert the tip of the dolphin probe into the tube I'm about to measure, and to generate a specially shaped acoustic wave that propagate down the tube. Each change in the cross-section of the tube generates a reflection that is propagating and captured by the microphone on the probe. The main principle behind this system is that every defect has its own unique signature. The main advantages of the APR system is first its speed. It takes less than 10 seconds to measure a tube, and also by using the fact that the sound wave that we are generating is traveling in the air inside the tube and not on the tube material, it means that we are not dependent on the tube configuration and conformation, meaning that any tube shape, U-tube, fin-fan, spiral, S-shape, and any tube material, stainless steel, copper, brass, PVC, rubber, you name it, can be inspected. Once the inspection is done, I simply go to the last main tab, the Report tab, where we perform the analysis of the results and the creation of the final inspection report. In the Report tab, I can look at the signals that I just generated. The APR is based on a comparative method, meaning that we are comparing the signal to a good reference. Any deviation from the reference is a defect. In this specific case, when I'm referencing tube number 3 with the calibration, I see a deviation from my calibration from my reference tube at around 1.05 meter. This is the signature of a blockage. What happens here is that when the cross-section of the tube is becoming smaller due to the blockage, my pressure increases. When the diameter is going back to normal, I have the corresponding decrease in the air pressure. Quantifying this defect is very simple. All I need to do is to generate the thresholds, and then I can see that a bit more than 50% of my cross-sectional area is blocked due to this blockage. So I can basically continue and manually analyze each and every one of the signal, but this is very time consuming and it also requires a great deal of expertise from the user. What we did instead is invested a lot of resources in developing an automatic analysis system. All the user need to do is to go over here and to press the Analyze Measurements button. When the automatic analysis is done, starts the user part of the analysis. All the user needs to do now is to go over the system alarm list and to verify the system findings. From knowing the signatures, the user can easily know whether we are looking here at a real defect or at a false alarm, and he can simply approve or decline the system findings. After gaining some experience with the analysis job, it takes only several seconds for the user to complete the confirmation stage of each defect. When the last fault is reached, all the user got left to do in order to print a final inspection report is to press the Issue Report button. But first, I want to show you also the fault distribution pie chart we've got. I can refresh it, and here I can see all the defects that were detected break by their percentage. Now let's print the final inspection report. The report can be printed either in HTML or at a PDF format. And here is how our report look like. We have some general inspection details in the beginning, and then we have the two-dimensional map with color codes for each of the defects that were detected, the legend, pie chart, and then the list of defects based on their type that were detected, the tube ID, defect location, and size. We can also have the various signals at the end of the report. The system also have a capability of showing a three-dimensional representation of the unit that was inspected, and you can see here with different colors all the defects that were detected and their exact location in the three-dimensional plane. This basically concludes our short